Today's webinar is entitled TasLab Engage, Industry Engagement to Identify Climate-Sensitive Decisions over Multi-Year Timescales. Our presenter today is Dr. Carly Tozer. Carly is a research scientist within CSIRO's Decadal Climate Forecasting Project based in Hobart, Tasmania. Her research focuses on characterising the ocean atmospheric processes influencing Australia's weather and climate, especially extremes. Coming from an engineer background and with consulting experience, Carly enjoys seeing her research being taken up and applied by stakeholders. She also enjoys engaging with end users to better determine requirements and to measure the impact and benefits of her research. So I'll hand over to Carly to begin her presentation. Thanks, Carly.
Great. Thank you, Sonia, and thanks everyone for joining me today. I guess just to reiterate what Sonia said, I'm Carly from the Decadal Climate Forecasting Project at CSIRO. I'm based down here in Nipaluna, Hobart. Nipaluna is the name of the region in which Hobart sits in Palawakani, the language of Tasmanian Aborigines, and I would like to acknowledge the traditional and original owners of the land on which I live and work, the Muanina people. So as Sonia said, I am presenting on TasLab Engage. This is a little case study that we had as part of the NESP Earth Systems and Climate Change Hub. So I'll be talking about that today. And I wanted to thank first up my case study co-authors, James Risby, Sonia Bluhm and Tom Remenyi, and also my other co-workers who are a part of the group I work with at CSIRO. So, whoops. Let's make sure I can move to the next slide. So what can you expect from today's seminar? So I'll start off by giving a bit of an introduction to the Decadal Climate Forecasting Project. And this will hopefully lead seamlessly into talking about the motivation behind this case study. I wanted to also provide then a bit of context to multi-year to decadal prediction, say relative to say weather predictions and long-range climate change projections. I'll then move on to talking about the actual case study, so who we spoke to, what we did, what the outcomes were. And then I also wanted to talk about what we've done since TasLab Engage, and so how we've taken the learnings and moved forward with those. Okay, so to start with, the Decadal Climate Forecasting Project has been charged with developing a multi-year decadal forecasting system for Australia. As part of the project, we have various activities that form the project, one of which is obviously the model development, so the development of the actual climate forecast model system. Another activity we have revolves around observations. Observations obviously form the basis of our climate models, so they're very important. So we have a focus on identifying regions we need more observations and actually going out and collecting observations. We have activities focused on atmospheric and oceanic processes, and what I mean by that is identifying the processes in the climate system that are predictable and making sure our models can capture those processes. We also have an activity that is focused on application, so identifying the utility of these sort of multi-year decadal forecasts. So as part of each of these activities, we have various goals. And so the goals that are particularly relevant to this case study are those that are part of the applications activity. And in particular, we have a goal. Oops, I really need to learn how to, there we go. We have a goal that is, our goal is to improve and advance the use of multi-year decadal forecasts in Australian industries. Our approach to achieving that goal is co-development. So we want to co-develop multi-year decadal forecast knowledge with stakeholders. So we think this co-development process is how we're really going to derive benefits out of forecasts on this multi-year to decadal timescale. And so obviously one part, or at least the first part of this process is to actually talk to stakeholders. So I've written here interview, but I mean, talk to discuss things with these stakeholders. So that obviously provides some of the motivation behind this case study. But beyond just the DCFP's goals and sort of the Australian perspective, we have, there is a broader motivation. So the Decadal Climate Forecasting Project is contributing forecasts to the World Meteorological Organization's annual Decadal Climate Prediction Centre, which in turn is contributing to the World Climate Research Programme's Grand Challenge on near-term climate prediction. And so one of the goals that, and so when I say near-term climate prediction, I'm talking about this multi-year to decadal timescale. And so one of the goals that are as part of this Grand Challenge is to look into the utility of forecasts on these timescales. So you can see here that we've got quite a lot of internal motivation and also a global motivation for engaging with stakeholders. So I wanted to change pace a bit now and provide a bit of context to multi-year to decadal forecasts, so relative to weather, seasonal prediction and climate change projections. To start with, I just wanted to confirm that the terms prediction and forecasts are used interchangeably. You've probably noticed that I've been switching between those terms anyway. Okay, so we've got here this timescale from weather prediction, so the daily, weekly timescale out to long-term climate projections. Multi-year to decadal forecast obviously sits somewhere in the middle here. So when we're doing predictions, we are focused on tracking the evolution of different features in our climate system. And so when I say climate system, I mean, the atmosphere, the ocean, sea ice, things like that. So we want to focus tracking the evolution of different features in the climate system. And so what I mean by that is, I'll give an example just to perhaps clarify what I mean. So one of the features we focus on tracking when we're doing forecasts is the El Nino Southern Oscillation. So I think you are all pretty aware of what that means, and the El Nino Southern Oscillation and its extreme phases, the El Nino and the La Nina. We know that El Nino relates to dry or drought times in Australia and long-term drought. And we know that the La Nina can lead to long-term wet conditions. So this is a feature of our climate that we focus on tracking when we're doing predictions, and we want to predict it. Oops, I seem to keep losing my ability to move forward there. Okay. So a bit more information. So I've pulled here out just the typical evolution. Sorry, I should say that when I say tracking in El Nino Southern Oscillation, we track it using sea surface temperature anomalies as one variable. And what I'm showing up here is the sea surface temperature anomalies that are associated with El Nino from April to December. So what you can see here, we've got warmer than average temperatures in the orange, red colours, and blue are the cooler temperatures. So you can see here that from April through to December, this sort of characteristic warm tongue develops off the coast of South America. So by the time we get to December, we've got this really strong warming of the sea surface temperatures here in the tropical Pacific. And this coincides also with some cooling of sea surface temperatures around Australia. So this is our typical evolution. So you can imagine that when we want to forecast El Nino, we want to make sure our forecast system tracks this evolution. And in order to do that, we need to make sure we start in the right spot. And so as an example, let's say we are in August right now. And if we want to do a forecast for December, so we want our El Nino to look like this. We want to make sure we want to track the evolution, and we want to make sure our model state starts looking something like this. So we want to start off here. If we want to get to December, we want to forecast December sea surface temperature anomalies. We want to make sure our we kick off our forecast model looking something like August. But what happens, for example, if we if our SSTs actually look a bit more like they do in April? So you can imagine that we might, if we're doing a December forecast, we might not actually look like what we should look like. So let's go a bit further. So what I mean by this, so if we're kicking off our model in August, we want it to look like something like this, so that we get our December forecast looks like this. So it looks like the typical evolution of an El Nino. But say our model starts off looking like this. Well, our December forecast, you know, it might look like something different. So it's probably not going to be a very good forecast. So I guess the point of all that is to highlight the fact that when we are doing forecasts or predictions, the starting point of our model is really important. So we need to get the initial conditions. We need to initialize our model correctly. We want to make sure that climate state is right and right for the particular feature we're tracking. So I think I might have summarized that here. And this is true of prediction, I guess, on any time scale. So you can imagine in the weather, we're tracking the atmosphere. If we had a front over Western Australia, you know, we want to make sure if we want to forecast for the next few days, we want to kick our model off tracking that front properly so that we can then track the evolution of that front to get a good forecast. So hopefully that kind of gives you some of the flavour of commonalities across predictions on timescales. So the key thing is that initial conditions of our forecast model are really important. Now, moving to the longer term, you might be able to think that it might be clear to you that, well, if we're, say, I'm going back to this El Nino example, if we're wanting to track El Nino and say we're in an El Nino now in August, but I'm going to look at 30 years, what's happening right now is probably not so important for 30 years' time. The same El Nino will not be relevant. It would have long gone. So as we move to longer timescales, the starting point of our model is less important, at least for El Nino. And when we're looking on the longer term, we're looking more about changes in the characteristic of El Nino. So maybe changes in mean SST, sea surface temperature anomalies associated with El Nino. We're not going to be tracking individual El Nino events. You know, when we get to the longer term, we're actually more related to sort of changes in statistics and how influences like greenhouse gases affect, say, the character of El Nino. So I hope that was a very sort of non-extensive review of, you know, predictions and projections. But I guess the key point is that when we are doing this multi-year to decadal prediction, our initial conditions are still really important. So that's a big part of what our modelling group is doing as part of the decadal climate forecast. They're working on an initialisation scheme to make sure we start our model in the right place. But when we're doing projections, we don't worry so much about getting that initial climate state right. We want to make sure the climate looks, you know, the statistics are about right, but we don't necessarily have to track that El Nino event. Okay, so I think we've probably talked enough about that, but hopefully that gives you a bit of an idea about where these predictions sit relative to weather and seasonal and climate change projections. Whoops, let's move on. Okay, finally got to the main event. So now I wanted to talk about the actual case study and give a bit of a background. So TasLab Engage focused on engaging Tasmanian-based stakeholders, and maybe that's a bit parochial of us, but you know, logistically we're based down in Tasmania, so it's easier in that sense. But perhaps more importantly, Tasmania provides a really good ground for exploring the utility of these forecasts. Tasmania has a broad range of industries in the region. We have hydropower generation, Antarctic operations, agriculture, emergency services, forestry, you name it. We also have a really interesting variable climate across a really small region. So there is lots happening in Tasmania, and because of that, we think of Tasmania as a laboratory for climate research, information and applications, hence TasLab, and hence our focus on Tasmanian-based stakeholders. Okay, so we had various objectives or goals we wanted to achieve with this case study, which I've listed here. I won't talk to all of these objectives, but what I want to focus on in this talk is these two objectives. So the key objective to identify and engage with Tasmanian-based stakeholders, and then our objective to get a better understanding of the climate-sensitive decisions stakeholders make, and particularly focused on the multi-year to decadal timescale. Okay, so who was involved? We targeted different industries, and we were really keen to talk to people who were involved in the operations side of these industries. And we interviewed the Australian Antarctic Division, State Emergency Service, specifically the Flood Policy Unit, Tasmanian Institute of Agriculture, the wine industry, and Hydro Tasmania. And I do want to thank very much the participants from those organisations. The time you spent with us was invaluable, so thank you very much. Okay, so interview design. We had about 2 hours with each of our stakeholders, and we started out with a list of about 30 questions. We didn't necessarily ask all those questions, we just used them as a guide to sort of to kick off discussion. And I think what was important to note is that we didn't, although we do have a key focus on the multi-year to decadal timescale, we didn't only talk about that timescale, we didn't jump right in. You know, we really were focusing on building a picture of the operations that, you know, are undertaken by each stakeholder, their climate sensitivities, the decisions they make on different timescales, and the types of information they incorporate into making these decisions. So we wanted to build a broad picture. So as I said, we spoke to 4 stakeholders, and what was interesting, we found some common themes across all of those stakeholders. The first of which I'll talk to today, the first of which are that extremes are really important for each of these stakeholders. You know, so we're talking like, and on different timescales, so we're talking heat waves, frosts, out to dry years, hot years, things like this. They're very important, and they have the greatest impact on the operations of that are undertaken by all of these stakeholders. We also noted that anecdotes related to extreme events or years do guide practice for these stakeholders. So as an example, you know, if there was a really dry year in 2015 and there were negative impacts to operations, you know, these are things like today we want to avoid what happened back in 2015. So we'll do things that will make sure we don't end up back where we were in 2015, for example. And I think what was interesting to us was that all stakeholders have a clearly articulated set of decisions they make on multi-year timescales. So I'll move on now to talking about some of the outcomes from individual stakeholders. I won't talk about wine, the wine industry. You can read more about that, and that's mainly as I guess a time thing. But you can read more about the outcomes of the discussions with the wine industry in the report, which is up on the ESCC Hub website. Okay, so let's start off. Okay, so I'll start off by talking about the Australian Antarctic Division. So the AAD is responsible for Australia's activities in the Antarctic Territory, which is in eastern Antarctica and the Southern Ocean. They operate 3 stations in eastern Antarctica. We've got here Casey, Davis and Mawson, and also Macquarie Island. And aviation and shipping dominate operations planning. So each year they send expeditioners down on the icebreaker, and also via plane. So various issues around, sea ice, it can cause challenges. There's an ice runway in Casey Station that is built each season. So, these are the aviation and shipping dominate the operations, as I said. Okay, so some of the findings in regards to current climate information use. The use daily to 5-day weather forecasts over summer. So I should clarify that summer is sort of the peak season of activity for the AAD. And so they, make decisions on a day-to-day basis about whether to fly, particularly whether to fly. So the daily timescale is important, and weather forecasts are important. They do make seasonal to multi-year decisions, but tends to be based on past experience. So I guess, this is where sort of past knowledge is important. You have this general idea about how the summer season will progress, and have general idea about, well, we will send first lot of expeditioners down on a plane to Casey in October, and then the first lot of expeditions down to Davis on the ship down in November, something like that. So there's this general idea about seasonal to multi-year planning. I also note that they did incorporate some knowledge from climate change projections, and that influenced the design of the new icebreaker, the Noyina. And so East Antarctica is projected to have more sea ice into the future, and so that drove them to make sure they increase the ice breaking capabilities of this new icebreaker. So for key climate variables, well, any climate variable that impacts shipping and aviation is important to the AAD. So we're talking things like sea ice extent and thickness, Wilkins runway temperature. If the temperature is warm, we're not going to be able to build the runway. We're not going to be able to fly from Hobart down to Casey. And obviously wind and cloud cover affect day-to-day aviation operations. So there was quite a lot of scope for using annual to multi-year forecasts in the AAD. As I said, there is this sort of, I guess, maybe typical annual cycle of aviation and shipping operations, when they send people down to Antarctica, when they build the runway, when each station is resupplied. In addition to those operations, they also regularly have multi-year or annual to multi-year projects. And one of these, for example, is a million-year ice core project. So there will be several years of scoping, and then several years of actually drilling the core. So these are other projects that require long-term planning. So I wanted to talk now, maybe give an example of potential forecast use. And so this example, I'm focusing on Mawson resupply. So this is my lovely ship track here. May not be accurate, I'm sure it isn't. And so we've got Mawson here. So the icebreaker will leave Hobart and resupply the station with food and fuel, and also personnel. But challenges arise with Mawson because there is often a lot of sea ice, and so the issues occur when the sea ice does not behave like expected. So perhaps it is, more extensive or thicker than normal, and the ship just can't get to the station. So when this happens, there is a risk that, you know, they might not be able to change over personnel. They may not be able to resupply the station. You know, the alternative might be to sit the boat off the station and use the helicopter to move people and move fuel over. But you can imagine that that is not very economical. And so, and, you know, when things like this happen, there's this whole sort of knock-on of logistics, you know, over a summer season, all these stations are connected. So if something happens at Mawson and, you know, the boat can't do what expected, things then also back up at Davis and Casey. So sea ice is a particular issue at Mawson, and I did actually have some examples. So this is a real challenge for the AAD. Okay, so we know that, you know, a forecast only really is useful when it will change a decision. So the forecast I'm talking about here is of greater, so if we're starting from this year, so next year the forecast is for increased sea ice around Mawson. The decision that they could change, well, this season they may decide to resupply the station with enough fuel and enough supplies to cover the following years. So we can hopefully, you know, if that forecast came true and we couldn't get to the station, we're at least geared up because we have enough fuel, we have enough food for the next few years. So that's an example how a multi-year sea ice forecast might be used by the AAD. Okay, so moving on to the State Emergency Service here, just a bit of a background. The SES provides emergency response services across Tasmania for storms, floods, road crash rescues and such. They also do community education programs. And our discussion with the SES particularly focused on operations related to flood response. So, as you can imagine, the SES is a reactive organisation. You know, it's emergency response. So, weather, flood forecasts, extreme weather warnings, you know, hourly, daily are really important for the SES. We also note that our representative indicated they have been using projections to look at some flood risk maps. The key climate variables are things associated with flooding, you know, rainfall, high rainfall, stream flow, tides and swells for coastal areas, wind, you know, knocking down trees. So these are all important. Scope for using annual to multi-year forecasts. And perhaps this is, I think this was kind of quite an interesting thing about the SES is at the outset, as I said, it's a reactive organisation, so wouldn't necessarily expect it to have sort of long-term decisions or there to be sort of utility of these annual to multi-year forecasts. But we did find that on the long term, the SES have decisions around volunteer recruitment and planning and community education programs. So, whoops. So this I guess forms our potential forecast use example with the idea that say we had a forecast over the next few years that southeast Tasmania would be wetter than normal. The idea would be that had the SES planned to do community education up in northwestern Tasmania, well, based on this forecast, they might think, well, we'll now focus on southeast Tasmania and make sure, you know, we've got our volunteer recruitment and education sorted. So that's an idea about how a long sort of these annual climate information might be useful to the SES. And I think, as I said, you know, it was perhaps a bit of a surprise that there might be some use of these long-term, these annual forecasts. And this really highlighted to me the importance of talking to people and you know, that's not the utility of forecasts was perhaps not where we thought it would be when talking to the SES. So that was a really important, it really highlighted obviously the need to talk to different stakeholders. So I'm moving on to Hydro Tasmania now. So Hydro Tas operate 30 hydropower stations across 6 water catchments, which are primarily located in Western Tasmania. Hydro provide electricity to Tasmania and also exports electricity to mainland Australia via Basslink. So talking about current use of climate information, they use information on all timescales. So on the daily to weekly timescale, spot traders use weather forecasts and also energy price forecasts. Interesting, they look at seasonal forecasts but don't necessarily incorporate them into their operational system. Their simulations are driven by historical climate data. Key climate variables. So as I said, a lot of the catchments are primarily in Western Tasmania. So rainfall in Western Tasmania, particularly, the extremes. So, dry periods in Western Tasmania are really important for Hydro Tasmania operations. Mainland temperatures, particularly, summer heat waves in Melbourne are really important because this causes price spikes. So this affects their operations too, or influences their operations. So scope for using annual to multi-year forecasts. So Hydro Tasmania have a very complex network system, and their simulations run on various timescales, including running out to several years. They do have a multi-year storage in their system, so there's certainly scope for incorporating multi-year climate information into those simulations. In addition, they also do network maintenance. So this is where they take storages offline. So smaller storages, I think, are typically undergo maintenance every 5 years, larger storages every 10 years. So there are long-term decisions around planning for those maintenance. And one of the examples would be that, if you had wetter than normal conditions, this really affects the ability of Hydro Tasmania to undertake maintenance, which would then cause issues and perhaps back things up and maybe mean that they have to take a storage offline at a time that they don't want to, at a time when they want to be generating electricity. So there's certainly scope also in this sort of maintenance side of things to incorporate multi-year climate information. So I will talk a lot more about Hydro Tasmania, but maybe to start with, I'll stop and do a little bit of a summary thus far from some of our learnings from TasLab Engage. So one of the key things that we came out with is that all stakeholders make some sort of climate-related decisions on the multi-year to decadal timescales, and perhaps some of those were surprising, for example, in the SES case. And what's important is that there is a need for targeted climate information. So, people need information that is very specific to their operations, and not every piece of climate information is important for every stakeholder. So we really need targeted climate information. And I guess the key learning is that these interviews or these discussions are important, but they are also only a first pass in establishing potential use cases. Whoops. So out of TasLab, we came up with some recommendations for the Decadal Climate Forecasting Project. And I mean, these were recommendations that the DCFP were sort of working towards anyway, but I think the outcomes from TasLab really helped, hone some of those recommendations. So I'll leave these up, but I guess the key one that I want to talk more about is this recommendation around continued engagement with stakeholders to explore where any areas of multi-year forecast skill could be used in stakeholder decisions. So this now leads me into beyond TasLab Engage. So this was not the name of the project, but this was an additional project we undertook to really attempt to apply some multi-year decadal forecasts to the Hydro Tasmania systems. And this sort of forms a part of a broader, much broader project with Hydro Tasmania. So this project involved the development of a toy version of the Hydro Tasmania system, and this toy version was developed by Michelle Ho, obviously with the Decadal Climate Forecasting Project, and also co-designed with Hydro Tasmania. So the co-design and co-development aspect was really important. So thank you for Hydro for being involved in this process. So this toy model allows us to articulate how climate information might change multi-year decadal decisions for Hydro Tasmania, and it really allows us to test whether hydro can actually derive any benefits from the input of future climate information. So, you know, it helps us answer questions like, well, how good, how skillful does a forecast actually need to be before it could be of any use? And, you know, so, you know, if we have a forecast with perhaps low skill, is that actually okay? You know, will there be a certain percentage benefit, and, you know, how much of a percentage increase in revenue is useful for hydro? So these are sort of the questions that we can ask using this toy version. And I guess because it is a toy version, you know, we can do simulations relatively quickly and change things relatively quickly. And as I said, this is definitely driven by Dr. Michelle Ho, who is a CSIRO colleague. So this is where I talk through some of just to show you the development of this case study and the types of things that we've done thus far with this model. This is my very crude representation, and Michelle has done a better job than I have, but just to give you the general gist of things. So Tasmania here, obviously, the mainland Australia. And so we've got some storages here in Western Tasmania. Hopefully you can see my little arrow here. So Western Tasmania. We've got a multi-year storage in Guyana Great Lake. So this system supplies electricity to Tasmania, and I'm just kind of representing, you know, this with this box here. So say industry in southeast Tasmania, for example. So it supplies electricity to Tasmania, and it also supplies to the mainland via Basslink. So that's sort of the general setup. So in addition to, I guess, the electricity demand, there's also, we've got some environmental demand. So we have environmental levels of the lake that we need to maintain for environmental purposes. So that's one thing to consider. And also that there is an irrigation demand. So these are, I won't sort of talk too much more about that, but that's just to give you an idea of what else needs to be considered in this model. And so our goal here with this toy system is to model the role of Great Lake, which is our multi-year storage in this system. So I'll move on now to sort of looking at a scenario or a forecast. So as I said, our key climate influences, which we spoke about during our TasLab Engage process, the key climate influences are rainfall in Western Tasmania and Melbourne temperatures. So I've represented them here. I clearly went a bit, got excited by the clip art, if you can't tell. So I'm going to talk through a bit of an example here. So say we had a forecast for a hot period in Melbourne, so perhaps next year or next summer it was going to be hot in Melbourne, so we're getting heat waves. Let's just say we had average rainfall in Western Tasmania. So as I said, heat waves in Melbourne, what we're going to experience then is a price spike. So hydro will want to generate electricity to sell into the market, national market, to take advantage of the price spike. So if we had this forecast here, how would hydro respond? Well, the response would be that they would bank water in Yingina Great Lake. So that at the time this hot period occurs, there is enough water in Great Lake so that they can continue generation and, as I said, take advantage of this price spike. Okay, so another forecast situation here is a forecast for a dry Western Tasmania. So these are obviously part of this system in here. So if we have a dry Western Tasmania, we can, we'll keep that up there. So we're not really going to be focusing on these systems. We don't we don't have the water here. So it's all about Yingina Great Lake. And so the decision would probably be not to sell into the national grid. So we're sort of cutting off Basslink here. And our goal would be, we want to reduce, so our reliance is very much on Great Lake. So we have the goal now to reduce low storage risk in Yingina. So if we have a forecast for a year in advance that, next year it's going to be dry in Western Tasmania. So these storages are out of play. This is our focus. We want to reduce the risk of the low storage risk in Yingina and Great Lake. So our response today, again, would be to bank water so that, again, we have enough water here to continue generating electricity, but also maintain our environmental water levels and irrigation demands. So this is just sort of a bit of a walkthrough and a very sort of crude walkthrough some of the decisions and like how multi-year forecasts might change decisions for Hydro Tasmania, and how we've used this toy model to test those decisions. And I should say I've got a little time series here, thanks to Michelle, just to give proper kudos to her work, my crude representation of the model. So we've got here just, if we see here, this black line is our observed storage in Great Lake. So this is just an example. And the idea is that if we input climate information, perhaps we can still, generate as normal, but we can avoid going into this minimum operating volume. So this is the type of thing we want to see. So if you can see here, this modeled storage is, it doesn't dip into this below this minimum operating volume. So I won't sort of talk too much more about that, but that's kind of the type of output that Michelle is looking at from this model. And so we can sort of build on this model and try test different things in this model. And I think this has been a really useful process to sort of go beyond just talking with Hydro Tasmania to actually looking at sort of inputting different types of climate information and different levels to see if we can derive any benefits for Hydro Tasmania. And by benefits, I mean, I guess a revenue increase with the input of climate information. So I'm not sure how I'm going with time, hopefully. I think I might be pretty well on time. So wrapping up now. So summary and future goals. We think that the co-design process, co-development process is really critical for deriving any potential use of climate forecast information. And I say climate forecast information generally because I think, on any time scale, we really need to talk to stakeholders and to really understand the decisions and the operations that they undertake. If we're going to derive any benefit from using climate information. For the DCFP specifically, we're sort of, I guess, taking this approach and participating or wanting to participate in the Tasmanian Climate Consortium. So that's something that has been driven by Hydro Tasmania. So it's a collective of industries in Tasmania who have climate sensitivities. So we want to make sure we're involved to assist with the characterisation of near-term climate risk for these Tasmanian-based industries. Beyond Tasmania, I guess a future goal is that we would like to engage with stakeholders outside of Tasmania in other industries, and just to get a broader picture of the potential utility of forecasts on any timescale, but particularly the multi-year to decadal timescale. All right, I think that leads me to the end here. I'll perhaps pass on to Sonia. Thank you very much for listening, and I hope you've gained something out of this seminar. Thank you.
Great, thanks Carly. Thanks for a really great and informative webinar. So we do have some questions coming in. I thought I might start off with Jodie's questions because it refers to your last comment, Carly, around looking to expand the stakeholders that you talk to in different industries and different states. And Jodie asks, she's curious to know if a local government within Tasmania would be an interesting sort of stakeholder to include in your future interviews for TasLab.
Absolutely, I think so. And I think that's if we take anything from the TasLab Engage is that we're not very, climate scientists are not very attuned to the types of decisions, people make. So it's really important to talk to them. And, as I said, with SES, we didn't sort of, on the outset, you wouldn't have thought that long-term or multi-year forecast would have been of any interest. So I think we are interested in at least having a chat to a broad range of people, including local government, and talking through the types of decisions and the types of climate sensitivities in their operations. So yes, definitely.
Great. So I guess something to note that if you do want to be involved, there's some contact details on the screen now. Get in touch and I'll pass it on with Carly and we'll go from there. The next question comes from David Caroli, who says, for the multi-year information, there are likely to be large uncertainties. Do you provide probability forecasts, and how are the uncertainties or probabilities estimated and provided?
That's a really good question, and I guess I didn't sort of talk specifically about uncertainties. So we are doing work with Hydro, and yes, things are probabilistic. We look at a whole range of skill metrics, and I think the thing, so we also provide our forecast more broadly to this World Meteorological Organization. I'm not quite sure about the types of uncertainty informations that are involved with that, but I feel like I've got a bit of a blank here. But we do provide, I guess, different. So for Hydro, for example, we provided different skill metrics, and I think perhaps the point of all this is that yes, there will be very large uncertainties with these forecasts, and the only way that we can, as I said, derive any benefit is to talk through these uncertainties and see with individual stakeholders and with their systems, and see whether despite these uncertainties, can they still change? Are they willing to change the decision given the uncertainties? And so we can only do that by working one-on-one. And so I think that's probably, I'm just trying to remember the types of things we've provided to Hydro, but my mind's a bit blank now. But I think my answer would be that yes, there are definitely a lot of uncertainties, and that would be the reason why we would go through this long process of developing these sort of toy models and looking through well, how good does a forecast need to be before you can get any benefit. And I think it's also about building trust with the stakeholders, knowing that climate forecasts in general have a lot of uncertainty. So we need to build trust with our stakeholders so that they can feel comfortable using the product despite its uncertainties. And I should say that also, sorry, blabbing on a bit here, but uncertainties change over time too. So I guess that's the key thing. So one of the ideas is that in, say, an El Nino event, our uncertainties, we have more certainty about how El Niños evolve. So our forecast uncertainty will go down. So relative perhaps, relative to when we're in another climate state where things are a bit more variable and we have less certainty. So as I say, these would be things that we would talk with stakeholders through.
And a question that follows on from that, which you may have sort of already answered, Carly, is from Neil, who asks, how skillful would the decadal climate forecasts need to be in order to engage stakeholder confidence out to multi-years?
Yes, that's a good question. And I think, again, we can only really answer that by talking to stakeholders. And I think it depends on also like the types of decisions. Are there decisions that hold less risk than others? And that was one of the really nice questions that we asked during this process is, what is the risk that you want to avoid, or what is the thing that you need to avoid? And so in your operations, and so maybe for the AAD, one of those risks is like the station closing down completely. So that is a risk that they want to avoid. So maybe for that decision, they would not want to rely on uncertainty in the forecast. But that said, maybe if they do decide to resupply Mawson, for example, more this season, but then sea ice conditions end up being fine the following season, maybe that's okay, and they can wear having that extra fuel at the station. So I think there will definitely be uncertainties, but the actual how concerning or relevant those uncertainties are might relate to the decision that the operator is making, and how willing they are to take the risk. But again, I think it's about building trust with people. I don't think this is a product you can sort of just hand over to people and let them use, because there are uncertainties involved.
One of the things, Carly, I got out of our conversations with the stakeholders as well was that they wanted to see some evidence of skillfulness before that they would uptake those forecasts. So they wanted to see a couple of years where they said, yeah, you've done pretty well, 70 to 90, 80% or something success. Now we trust you, now we'll take it up. And it was about that trust, not only with the information, but with the organisation providing the forecasts as well.
Yeah, absolutely, Sonia.
So we have a few more questions coming through. So Esther asks, and this might put you on the spot, Carly, but she wants to have a little bit of a summary information around the wine industry. What kind of climate information were they interested in, and how did they apply that to yield and planning? Are you able to give just a really brief 2-sentence summary on what we found?
I clearly am not very brief, if you haven't noticed. So the wine industry, one of the key, I guess, climate variables was temperature. And temperature on different timescales. So frost is an absolute killer. So that's a daily timescale. But then, long-term temperature projections were really important. And so in Tasmania, it's almost been, I guess, favourable, if I can say that, this warming trend, because it's mean they've been able to grow in areas perhaps they weren't able to in the past. So I think one of the key, if I recall, wine is a long term. Vineyards are set up, 50 years. So projections were quite important for them, and also the daily timescale. If I recall, they're relatively sophisticated and users. They've been using climate information for a long time. The seasonal timescale was relatively important, and the multi-year timescale. They had decisions around purchase in Tasmania. They had decisions around purchase of sort of a fungicide, if I recall correctly. So these are things, and it was connected to the mainland. You know, there were challenges around getting enough fungicide if there's, I think, really wet on the mainland and all the fungicide is purchased up there. You know, there could be challenges down in Tasmania. So I think one of the challenges was that the growing season in Tasmania was a bit out of sync with the mainland. And if my memory serves me, yeah, there was some potential, the potential use revolved around this sort of fungicide use and, you know, when to purchase it and how much to purchase depending on climate forecasts on the mainland and so on. Hopefully that answered the question.
Thanks, Carly. Yeah, and Esther as well, I've posted a link in the chat to the final report from the case studies, so there'll be a lot more details around the wine industry in that report for you there as well. Another question comes in from Juliet around were there any stakeholders reliant on groundwater given the wide timescales in hydrogeology?
That's a really good question, and that was not something that came out of any of our interviews. So none of the people we spoke to. Well, and I mean, I maybe now I'm showing my ignorance of the hydro system. Perhaps there are some, you know, there's groundwater fed springs and rivers, but we didn't talk specifically about groundwater. But yeah, I'm sure that would come into play for certain industries because of the longer timescales that we're interested in. But yeah, nothing with the stakeholders we spoke to for TasLab Engage.
Thanks, Carly. The next question comes from Bob, who says that the decadal climate forecasts are useful for operational decisions and long-term climate change projections for big investment decisions. However, do you find that your users might be interested in the decadal climate forecasts to influence timing or staging of big investment decisions, as confidence in such decision-making is often especially influenced by short to medium-term experience and outlook?
Yes, I would think that they would definitely come into play, and I guess hopefully related to this is this idea that I spoke about initialization of climate forecasts, and so as we move longer term, we sort of lose sync with the climate, but that doesn't mean that that information isn't useful. So as part of the Decadal Climate Forecasting Project, we're doing what we call large ensembles. So we've got a really, so we've got about almost 100 versions of the Earth, essentially, of our climate system. And so we can use this climate ensemble to better understand the statistics of the climate going into the future. So we have a lot more data to play with, and so we can, you know, provide perhaps more information about the risk of, you know, changing rainfall or temperature statistics, and this information, I think, yeah, from this 1 to 10 year I would think would certainly be useful or could be used to guide these sort of, you know, longer term investment decisions that are made by industries. Hopefully that was something of interest.
Yep, thanks, Carly. That's great. We have run out of time. I know that there are still a few questions that are left unanswered, so sorry about that. There are the contact details up on the screen, so if you do want your question answered by Carly and her team, just send them through to that inbox account there, and I'll make sure that we get a response to you as soon as possible. But for now, that brings us to the end of the webinar. So thank you to Carly for a really great webinar, and thank you to all the attendees for your time and interest and the fabulous questions that you've sent through. Just a reminder that a recording of today's webinar will be provided on the Earth Systems and Climate Change Science Hub website, and a link will be provided to all attendees of the webinar today in the next couple of days. If you have any questions or inquiries about today's webinar, again, please don't hesitate to contact us through those details on the screen. I'm more than happy to engage and help out. And finally, look out for emails and information about the next Earth Systems and Climate Change Science webinar for next month. That webinar will be looking at scenario analysis of climate-related physical risk for buildings and infrastructure, and it'll be using the soon-to-be-published guidelines from the industry-led Climate Measurement Standards Initiative. So more of a finance focus for next month. So thank you once again, everyone, for attending, and we look forward to seeing you at the next Earth Systems and Climate Change Hub Science webinar. Thank you.
Thank you.